So good evening once again, everyone. So we are into the last session, session 13, and day 6 of our faculty development program, Next Generation Electronics and Communication Systems empowered by ML and AI. So today for the last session, we have Dr. Akhilesh with us. Before we start, let me give you a very brief intro about him. So Dr. Akhilesh Verma received his PhD degree in Electronics and Communication Engineering from Delhi Technological University, Delhi, and masters on P5 antenna for wireless application from NITTTI Chandigarh. He is currently working as a research scientist at Department of Electronic Systems and Sensor Technology, Brandenburg University of Technology, Korsberg, Germany. He has worked at Aquila Technologies and Integration Solution Private Limited, Noida, India. He worked as a senior engineer R&D with the Bhumi and Tech Equipments Private Limited, Delhi, India, and as product engineer at Senos, Riga, Latvia. Over the years, he has developed several fully 5G antennas based on artificial magnetic conductors to reduce SAR and achieve high gain and beamforming beam scanning through non-uniform periodic metasurfaces. He has authored over 21 journals and conference papers. He has also been granted one patent on 5G antennas. His current research interest includes metasurfaces, artificial magnetic conductor AMC, SIWSF mixers, power amplifier, lumped and microstrip filter design at KU band, lumped filter design for radar applications, lumped and active antennas for 5G applications, GNSS antenna design, and the use of AI in these methods. Dr. Akhilesh Verma is also working as a mentor at University of California, San Diego, US. He is appointed as an industry expert in advisory committee of SETCOM Lab, NSUT, Delhi, India. He is also working as a consultant at as senior antenna engineer scientist at Rasoft, California, US. So with this brief bio, I'd like to welcome Dr. Akhilesh. Now I hand over the session to you, sir. Please share your screen and then you can go ahead.
Thank you, sir. Thank you for the introduction and giving me this opportunity, this platform to share my experience and expertise in this talk. So I'm just going to share my screen. Is my screen visible?
Yes, sir. Screen is visible.
Okay, thank you.
Yeah, it's good to go.
Yeah. So the topic of my talk is RF transceivers design with beamforming antenna for satellite applications. And this is the content I will cover in my slides, introduction and motivation of this talk, and fundamentals of RF transceiver design, beamforming antenna concepts, and application of AI ML application in beamforming, and RF front end with the integration of beamforming technology, and then I will conclude my talk. So yes, so this is the overview of modern satellite communication systems, and as we know that the requirement of the connectivity and the modern satellite communications networks evolving rapidly. The satellites are typically categorized based on their orbital altitudes, like geostationary Earth orbits. It is about 36,000 kilometers, and fixed relative positions to the Earth's surface, suitable for broadcasting and continuous regional coverage like weather forecasting and television networks. And its latency is very high. It is about 250 milliseconds, one way latency, which is real time applications. And the next is medium Earth orbit, whose is 2000 to 20,000 kilometers range, and its latency is lower than the geostationary Earth orbit. It is 100 milliseconds. And the applications we use MEO is for navigation constellations like GPS, Galileo, GLONASS, and the low Earth orbits 500 to 2000 kilometers, which is very interested area now, which basically we design the satellites and CubeSats mostly for that orbits, low Earth orbits. It latency, because its latency is very less. It is less than 50 milliseconds as compared to other orbits of the Earth, like high data rates and global coverage through multi-satellite constellations, and used by the modern broadband systems Starlink, and OneWeb and Telesats. So basically the CubeSats, and these are the small satellites, miniaturized satellites, typically 1 unit to 12 unit form factors, and it is very cost effective because it is very small, very nano satellites, which is used for the communications and remote sensings and scientific missions. Even NASA has sent many CubeSats for the different uh, missions, and it increasingly used for educational purpose and research missions. And this is the example. Right now I am handling the project OA5 project, which is 3 units CubeSat for uplink and downlink frequencies to establish the link for 5G applications. So you can see the figure where, which is the 1 unit CubeSat and 1.5 unit CubeSat, up to the 12 CubeSats units. So as we increase the number of CubeSats, the power consumptions also increase. So we have to see all other aspects, because when we increase the CubeSats, we need to see the requirements and other factors, like the bandwidths and the range, and the most important thing is power consumptions, which is very crucial points when we design any CubeSats. And according to the power consumptions, we use all the subsystems to design this whole CubeSats units. So how these satellites improving the communications? Because of the satcoms, you can able to call your loved ones where you are, on a cruise ship in the oceans and driving in the middle of nowhere, or hiking up a high mountains. So through these pictures, you can see that these are the ground stations antennas, ground stations, and user terminal equipment, which can be anywhere. And these are the constellations of the satellites, and these are interlinks also to each other. These satellites actually. So with the help of these satellites, it can cover the range anywhere, because of the connectivity. Uh, the key points of the satcom is like global connectivity, and they have low latency and broadband services, and mobile network expansions, and you can share the data in real time, and resilience, situational awareness also, and control over the autonomous vehicles. So how we select the frequency bands, and how it affects the satcom performance. So this is the band, you can see through this figure, which explain that L band, S band, and C bands for the different applications, like L band and S bands mobile applications, and C band for telecommunications. And for radar applications we use X band, and this is Ka band, basically we use for low earth orbit and high speed internets. And above that, like V and Q bands, low earth orbits and high speed internet speed. And above 100 gigahertz, like W band and G band, we use for the millimeter wave applications. So if I talk about the L band, which is 1 to 2 gigahertz, it offers good penetrations through the foliage and the buildings, and making it suitable for the mobile applications. Because the bandwidth is too low for the high data rate applications. Then we go for the C band, the 4 to 8 gigahertz, and its resilience against the rain fade and atmospheric absorptions make it suitable for telecommunication, because this band is less affected by the atmospheric absorptions and the rain fade also, but it is hampered by its narrow bandwidth. This is the limitation. And if I talk about the Ku band, which is 12 to 18 gigahertz, so more bandwidth make it suitable for video and broadband applications. And its antennas are smaller, because lambda equal to C over F. So frequency increase, then wavelength will be decreased. So it is affected by the rain fade when we go to the higher frequencies, or even at millimeter waves. So this is the limitations also when we go for the higher frequency bands. And Ka band, which is 26.5 to 40 gigahertz, it is widely frequency range, enables very high data rates and bandwidths. However, atmospheric absorptions by water vapors affect some frequencies badly. So this is the limitation at this frequency band at Ka band. and it is more suited to low Earth orbit satellites since they have less atmosphere to traverse. And the Q band, which is 40 to 75 gigahertz. Again, the wide frequency range enables very high data rates, but oxygen absorption at 60 gigahertz is a major concern. So this is a basic RF transceivers design. We know that this is if I go to this the lower chain, which is the transmitter chain, transmitting sides, we apply the signals, modulating signals with the amplifier. Then we use the IF filters and mixers, which up converting the frequencies, and then we use the image rejection filters to remove the image frequency, because sometimes mixture is confuse the frequencies IF or image frequency. So that's why we have to use this image rejection filters after the mixture. And then we use the some driver amplifiers to drive the main PA, and then we transmit the signals with the help of the duplexers, which is just like a MEMS which switch between the TX and RX chain, and then finally we transmit the signals through the antenna. And at the receiver sides, we use the LNA low noise amplifier, which is very important, and I will explain this in the next slides, which suppress the noise from the signals and then pass the signals with the amplification. And then we use this image rejection filters, and then we use mixers for down converting the signals. Like if we are receiving the RF signals, for example, we are receiving the signals like 20 gigahertz something, and we need the IF at 2.4 gigahertz, then we will down converting the signals, and we will apply the LO signals from here, and then we will use the IF filters and again this amplifier, because as we pass through this passive component, some you will lose the power, then IF filters, and further we use the amplifier to amplify the signals, so that the signals can be processed very easily in the digital section, like modulation or demodulation things we do. So this is the basic architecture of transceivers, any transceivers we use in any communication networks. So firstly, I will go through the receiver chain, because this is the most challenging part of any transceiver is the receiver chain, because we have to catch the signals, and then further we have to process the signals, because whatever we receive the signals will be with the noise and some interfering signals. So we have some challenges to remove these noises from the main signals, and that's why that is always the challenge to work on the receiver side, because if you work at the TX sides, you just have to transmit the power and you can uh, handle it very carefully. But when you work on the receiver side, so it's really the problem, because there are a lot of challenges at the receiver sides, the signal to noise ratio, noise figures, and you have to remove these noises from the atmosphere, so that you can extract the main information from the signal. So yes, yes. So the antenna part is one of the most important part of any communication networks. Either you are transmitting or receiving the signals. If you don't have the good performance antenna, then you will lose the signals, and even you cannot transmit the power properly if the antenna is not properly designed. So antenna is very basic, and just like a transducer which just convert the signals from EM to RF and RF to EM. So must provide the high gain and the directional sensitivity, especially for the satellite applications, which is very crucial in that application. So these are the antennas basically we use for the satellite applications, like parabolic reflector antennas, which is used for the highly directional gain antennas, and horn antennas. Sometimes we use its bandwidth is very wide, but there is a trade-off of the gain. You will get a low gain, but the bandwidth will be wide in that case. And the helical antennas, microstrip patch antennas, these are very widely used antennas for that applications. And phased array beamforming antennas, and this is the recent things we use in the satellite. to cover the maximum coverage for the proper providing the network to all user equipments. And slot and waveguide antennas, yes, and these are some passive beamforming antennas which designed by myself, and these are not active antennas. These are only the passive beamforming antennas where you are not using any active elements for beamforming applications. Like I'm not using here any phase shifters and any beam switching networks. So I have used some specialized materials like artificial magnetic conductors, which increase the gain of the antenna bandwidth also. And furtherly, I have used some superstates materials over the antenna with the AMC. It further increase the gain. And these are the non-periodic structures of the metasurfaces which I have used over the antennas with the AMC, because artificial magnetic conductor increase the gain, and these non-periodic structures basically scan the beam, which help to steer the beam in any direction. It depends how you design these non-periodic metasurfaces structures. And this is one of the antenna which is designed at millimeter waves, and its size is very small, very compact. You can imagine like your thumbnail size. And in that antenna I have used some RF absorbers like EcoSorb absorbers, which are very helpful to achieve very good VSWR and suppress the surface waves and improve the signal quality of the signals. And if it depends how you use these RF absorbers. With the help of these absorbers, you can split the beams in the different directions. It depends on the optimization, how you optimize your antennas. So with the help of these slices of RF absorbers between the substrate and patch, you can split the beams into two directions or three or multiple directions. And this is one of the antenna which is designed at millimeter waves using some structures like EBG and SIW structures. And this structure is designed in such a way that you will achieve the beam scannings from -60° to +60°. And this is two-port device actually, MIMO. Yes, so this is the receiver chain. When we go to the receiver chain, you will see the antenna actually uh, to receive the signals. So when we receive the signals, this signal is very weak, and we have the signal power and the noise power also, which is KTB. K is Boltzmann constant, and T is the temperature, and P is the bandwidth of the signal. So PS should always be greater than PN. Then we can extract the information from the received signals, and then signal pass through the antenna and go to this LNA. And why we are using this RF processing unit? It process the signal actually. It's remove the clutters and jammers and noise, you can say. There are different terms you can use. So after removing all these noises from the signals, then it passed to the baseband and modulations units, where you have the ADC and TAC things, so that you can process your signals easily. So you will get here the filtered fine-tuned signals without any noise. So sometimes you receive the signals at the receiver around -100 dBm, even -120 dBm. So it depends on the performance of the receiver, how you design it. If your receiver sensitivity is good, so that it can receive the signals at very low power like 100 -100 dBm, and signal is corrupted, has noise also. So we have to reconstruct the informations out of very weak signals. So because of that challenges and limitations, we have to amplify the signals while suppressing the noise from the signals. So that coming weak signals can be amplified with the help of low noise amplifier. And you can see that figure where the antenna is connected to the LNA and then ADC. Even you can connect directly the ADC to the antenna, but why you cannot do that? Because you get a very small and tiny signals from the atmosphere, and however ADC require higher input signals. So that's why, and so that the received signals can be converted to digital, because ADC can process the signals of the high amplitude. That's why we use LNA between the antenna and the ADC. And there are so many RF subsystems between the antenna and ADC. I will go one by one. What are the aim of the receiver? So yes, these are very important terms when you work on the receiver sides: noise, signal to noise ratio, noise figure, and the types of noise. So thermal noise is like Pn equal to KTB, and this is the value of Boltzmann constant. And if you calculate for the 200 kilohertz bandwidth, then we are getting this minus 121 dBm. So radio frequency interference, unintended emissions from the lightning and switching mode power supplies, etc. And circuits like thermal and source 1 over F quantizations. Example for the resistors, we have this value very common expression like Vn equal to under root 4 KT and receiver needs always Ps greater than Pn to demodulate the signals. That's why we have to remove these noises and clutters from the received signals. And if I talk about the FM broadcast, so signal to noise minimum noise ratio should be 10 to 20 dB for FM broadcast, and for if we go for the space and we use the BPSK binary phase shifting modulation technique, it should be 3 to 10 dB. This is the range. You cannot go beyond that and not below that. So, and noise figure, we know that this is the ratio of at the input signal to noise ratio and the ratio of signal to noise ratio at the output for front end or full receiver. So through this picture, you can easily understand how we see the signal to noise ratio and noise figure also. So this is the antenna, this is the transmission line we use between the filters and antenna. This is the pre-select filters, because if you have to receive the signals, and the signals should have some certain bandwidth of interest. So you don't want to receive the unwanted bandwidth of the signal, so you just use the pre-select filters. We just pass the specific band of frequencies which you required, and after that you use the low noise amplifier. So you have the some gain value lose here minus 1 dB, and you lose some gain in this filter, because filter is passive device. You will get you lose around minus 2 dB power here, and the gain of the LNA here is 10 dB. So if you see here, this is the power you received after the antenna. This is noise floor, like its amplitude is 1 and 4 is the amplitude of the received signal. And if you calculate, this is the signal to noise ratio, 4 over 1 is 4, and if you calculate in dB, it will be around 6 dB. And after this pre-select filter, uh, you will get lose the 2 dB power, so it is almost half, 4 to 2, right? So signal to noise ratio now is 2 over 1 is 2, and in dB it is 3 dB. But after passing to the LNA, you will get the high amplified signal. It is now the 20 dB and noise is at 12. So noise is added by LNA, because noise, there is some noise also added by LNA, but it's not much as compared to the noise in the received signals. So it is not much, as it is negligible. So here is signal to noise ratio is 1.67 and in dB is 2.2. So if you calculate signal to noise ratio at input and output, it is 4 by 1.67. This is the noise signal to noise at the input, which is 4, and this is the signal to noise ratio at the output, which is 1.67. So it is 4 by 1.67, it is 2.4, or in dB it is 6 dB minus 2.2, it is 3.8 dB. So this is the signal to noise, or you can say noise figure is 3.8 dB, and in magnitude it is 2.4. So frisk noise figure calculation, which is very important expression we use when we calculate the noise figure of the whole systems, because there are multiple components and stages in the receiver chain, like the band pass filters and LNAs. Again, we use band pass filters or image rejection filters also, and mixtures, then band pass filters and some amplifier for the amplification purpose. So, and they have some gain and some noise figures and noise factors, and we have to calculate the overall receiver noise figure. So this is the expression we calculate the noise figure of the overall system. So this is like f1 plus f2 minus 1 over g1, and it is continued. So if you calculate this, so you can put the values in this expression like this, and you will get the noise figure of the overall system is 8.3, and if you calculate in dB, it is 9.2 dB. So the observation from these values, like noise figure is 9.2 dB. It is the losses ahead of LNAs. If you see the losses ahead of LNAs, degraded the noise figure significantly. So front end usually set controls overall receiver noise figure and need to increase LNA gain and or lower mixtures noise figure. This is the thing you can do. The first thing is you can increase the gain of LNA. And second is you can lower the value of noise figure of the mixture, right? Because mixture also adds some noise or losses. So LNA amplify the signals, but it will not add much noise into the systems. As I told you, the noise is very less as compared to the noise received in the signals, and it is just located immediately after the antenna to maintain the signal to noise ratio. Because you receive the very weak signals. If you don't use the LNA just after the antenna, then you will lose the signals, right? So we have to use the LNA just after the antenna so that we can receive the signals with the amplifications and suppressing the noise. So noise figures typically should be less than 1 dB for high quality LNAs, and there is a trade-off. If you are getting the high gain, then there is some power consumptions and you will lose some linearity. So this is the trade-off you have to see over this while you are designing any receiver. It depends the requirements for your any system design. And technologies we use gas and GaN based commonly used for satellites. LNAs due to low noise and high frequency capability. So the second aim of any receiver is the dynamic range. Because when we use the LNA just after the antennas, we have to increase the gain, and we have to something to control the gain of the system just after the LNA. So we use a variable gain attenuator here, right? So we have the requirements of high dynamic range and its variable gain of 0 to 100 dB. And we know the ADC, analog to digital converter detection range is 6 dB per bit, right? So what it does, it adds the low gain when it is near from the base station, and it adds the high gain when it is far from the base station. So this is the functionality of this variable gain attenuator. And power consumptions also increase if number of bits increase, right? So implementation of VGA at RF is very challenging, and interfering signals limits the sensitivity of the systems also. So if it limits the sensitivity of the systems, then this is the challenge to extract the information from the received signals, right? So sensitivity should be improved. So this is the third aim of the receiver, down conversion. Because you don't use the frequency you received from the signals, right? So we have to down converting the signals. Just I told you in the previous slides, like if we are receiving the signals about 20 gigahertz or 24 gigahertz, but you have to process the signals at 2.4 gigahertz or something 1.2 gigahertz, then you down converting the signals. It is a down conversion. We called it down conversion actually. So baseband frequencies are lowered compared to the RF frequencies, and it reduces the power consumptions, right? So for example, the carrier frequency is 2.4 gigahertz and IF is 100 megahertz. So we have to use the local oscillator frequency is 2.3 gigahertz. That then we will get this IF frequency 100 megahertz, right? So because when you down converting the signals, you have the RF signals at the input of mixer, and this is LO signals, and this is the IF at the output of mixture. So IF basically RF minus LO, right, for the downside, and sometimes it is upside like LO minus RF. So that's why RF signals always greater than baseband, or baseband is less as compared to RF, and it can be achieved with the help of mixture or multiplier. Mixers basically add or subtract the frequencies you apply at the two inputs, and you get the output at the third port, because this is three terminal device. As I told you, the RF at the input and LO we are applying from here, and at the output we are getting the intermediate frequency, which is the RF minus LO. That's why we get the IF 100 megahertz here, because the carrier frequency we are applying 2.4 gigahertz and LO is 2.3, so you will get around 100 megahertz here. So mixture basically translates the frequency. It is translating the frequency, right? So we are receiving the 2.4 gigahertz, and we from the antenna sides, and at the output we are getting 100 megahertz. So it's basically translating the frequency. And noisy, it is noisy less, because noise figure around 10 dB, and sometimes you decrease the noise figure of LNA mixture, right? So like 7 dB or 5 6 dB, but it is not much go down below 5 or something. So yes, and require the image rejection filters. As I told you, sometimes mixture confuse uh, between the IF frequency and the image frequency, because you get the IF frequency from LO minus RF, and you get the image frequency like LO minus IF. So you will get the same IF from the image frequency also. That's why mixers confuse between these. That's why we have to use image rejection filters after the mixture, so that uh, it can distinguish between the signals. It is IF or image rejection uh, frequency, image frequency. So LNA can be work in high gain mode or low gain mode. So it is depend on the application. We need the high gain or low gain. So this is the fourth uh, aim of the receiver is filtering, right? Because after down converting the signals, you will get some component of the frequencies, and you don't require that, right? You need the desired one. That's why we have to use the band pass filters, and you can say the filtering filters after the mixtures, so that you can get the band of frequencies of interest, so that you can increase the gain of this particular band which you required, and you can extract the information from the signals in ADC. So presence of in-band interferences is very challenging, because it's always difficult to remove the noise within a band, because sometimes noise amplitude is greater than the signal amplitude. So, and the image frequency and IF frequency distinction, right? So compression will reduce required signal to noise ratio at the output, and require the sharp filters to suppress the unwanted signals, interference, and you can say the blockers. So effect of interference and jammers and blockers, it affect overall systems for performance. So this is one of the challenge here. And due to the compression, 1 dB compression point, the gain of the signals also reduced by 1 dB. Sorry. So the noise figure of the receivers increases, and intermodulations will lower the sensitivity. So your receiver sensitivity will get lower because of the intermodulations like f1 minus f2, right? This is the things we required. Then you will get f1 plus f2, then you will get f1 minus 2f1, or f1 plus 2f2, f2 minus 2f1. So these are the intermodulations which you don't require actually. So because of these intermodulations, the sensitivity of the receivers get lower. So that is the receiver part, down converting the signals. Now, the beamforming antenna concepts like the phased array antennas, which means you scan the beams electronically. You are not doing this by mechanically. You have seen the many antennas mounted on the vehicles on the radar, and they move mechanically with the help of some motors, right? But in case of phased array, the beam steering is achieved with the help of the electronically scanned array, a computer controlled array of the antennas, which create a beam of the radio waves that can be electronically steered to a point or in a different directions without moving or mechanical rotations in the antenna systems. And how we achieve the phased array and how it is different from the simple antenna arrays, because I have shown you my own passive antennas where you are achieving the beam scannings without using any active elements. So in the simple antenna arrays, you use the arrays of the antennas, and you don't have any active components in the antenna arrays, right? But in case of phased array, you will use some phase shifters, some attenuators, power amplifiers, right? So with the help of these components and the active components, you called it phased array antennas or electronically scanned arrays, because you use the phase shifters to shift the beams in a different directions without mechanically rotations of the antenna system. So you can see the radiation pattern. This yes, radiation pattern of phased array of 15 antenna elements, which is spaced by lambda by 4 apart, and phase difference between the adjacent antennas is swept between minus 120 to 120 degree. This is the scanning range of this antenna array. And the types of phased array like passive phased array, active electronically scanned arrays, and hybrid beamforming. You use the analog and digital parts in the antenna systems, then you call it hybrid. And digital beamforming is like this is completely digital beamforming. So yes, it is expensive when you apply the independent signals to the each radiating elements to the multiple elements to steer the beam in a desired direction. So it costs more when you use the different signals to steering the beams of the different elements. Then you use the phase shifters at each elements to steering the beams. So same signals you can apply here, and this signals is passed to the different phase shifters which change the phase of the elements, and it steer the beams, and it can coverage to the user A, user B, and user C, right? So beam can be steered in a different directions with the help of the phase shifters at each elements, and the signal's amplitude should be same. So only one single beam can be sent at a time, right? So or using the multiple beams with the four radiating elements, more energy signals can reach to the user. And what is the principle of this phased array? So you can see this expression phi equal to beta d cos theta plus alpha. So phi is the phase and d is the space between the elements, and alpha is the initial phase. So you can change the distance interspacing elements between the elements and the initial phase, right? So beam can be steered by changing the spacing between the radiating elements, that is d, and by changing the wavelength and position of beam can be shift in any direction. So if we restrict to change the wavelength and space distance d, what we are the options having the options that you can change the initial phase of each element, that is alpha, and with the help of that you can steer the beam in any direction. So this is the basic building blocks of the phased array, right? You use a power splitters, and with the help of power splitters you split the signals in the different attenuators, different phase shifters at each TXR exchange and at the output antenna element, right? So you just you just create the constructive interference, or you can say the wavefront, constructive wavefront, and with the help of this constructive wavefront it will combine and steer the beam in a direction, in a desired directions where you want to steer the beam. So what are the advantages of phased array? So it is very fast change of beam directions and high beam agility and high antenna gain, large side lobe attenuations, and multifunction operation by simultaneously generation of multiple beams. and failure of some components does not result in a complete system failure. So this is one of the most important advantage and privilege of the phased array. If some system fails, at least you will get some beam steering in some directions. The whole system will not fail. Disadvantages like the antenna radiation pattern deforms during beam steering. Yes, while steering the beam, you will get some side lobes. So this is the challenge while designing any phased array. So we just use some techniques to suppress these side lobes, like you use the non-uniform amplitudes of the signals, and you give the power to the elements which give the signals in a both side directions or broadside, and you decrease the power of the elements which basically giving the power in the side lobes. So you can use these techniques, and you can use some window functions also to suppress these side lobes. And yes, another disadvantage is like limited scanning range, uh, up to the maximum 120 degree in azimuth and elevation, and low frequency agility, high cost, and very complex structure. So these are the some possible arrangements of the phased array. Like this is the pictures of the linear array, and this type of phased array antenna designed by lines, and it is controlled by single phase shifter, right? So these arrangements of the arrays such that the number of linear arrays placed vertically to each other to form the flat antennas, right? So you can see these antenna arrays placed over one another, vertically placed, and each chain have its own phase shifters arrangements, right? Single phase shifters. So this is very complex and very costly also. You have to use the individual phase shifters for the each chain of the antennas array. So this is the disadvantage of linear array, phased array, right? Yes, arrangement is simple. Yes, disadvantage beam steering is possible in single plane because you can see these are placed vertically, so you will achieve the beam scanning in a single plane. Examples like PAR-80 horizontal beam deflections and FPS-117 vertical beam deflections. These are the examples of linear array which are practically used, and these are the models PAR-80 and FPS-117. And large vertical apertures and SSR antenna with fixed beam pattern. So yes, the planar array phase shifters per elements, and all the elements are arranged like a matrix which form the complete structure of the antenna. And okay, yes, and the advantage is beam direction in two planes, and disadvantage is large number of phase shifters, like an FPS 85 and Thomson Masters A. This is the model of planar array practically used, and these are different types of phase shifting methods you can do by changing the frequency and changing the length, and by changing the permittivity, dielectric constants, and by changing the permeability. So you can see here, just achieve the frequency scanning phased array. You just changing the frequency because lambda equal to C over F. And in this phase array type, beam steering is controlled by the frequency without using the phase shifters. As you change the frequency, your beam will be shifting into the different directions. Yeah, you can see here at the different frequencies, the beam is steering in a different direction. And by the phase shifting by changing the length, yes, because length, if you change the length, then it is also introduce the phase shifting by varying the feed length, right? Yes, and how AI ML assisted the beam forming, because nowadays we are using AI ML in different domains, and everywhere we are using AI ML. So why ML for beamforming? Because the rapid adaptations to change the channels, right? Like mobility, blockage, interferences, and beyond the classical model-based systems, and reduce onboard computational load by learning the compact mappings from the observations, and while using the different beam weights. So this this is the things we can use in the beam forming, because we have to see the different antenna patterns we can use, and the different beam scannings we need in our applications. So we can use ML for beam forming. And the major research directions like dynamic beam selections, scheduling the beams, and RL supervise, we supervise the networks to achieve the beam selections, dynamic beam selections, and interference mitigations via learned pre-coders and null steerings also. And learning the base calibrations, compensate gain and phase errors, and data-driven channel estimations for sparse and millimeter waves and K-band channels. So hybrid analog digital controls using ML to choose sub-arrays and digital weights. I will also explain the sub-arrays in my slides, in the last slides, I think. So yes, so AI for dynamic beam selections and interference mitigations. Dynamic beam selections like map low dim features like RSSI, right? Received signal strength, interference per sectors, UE locations, and coarse angle of arrival, beam index. And what methods we use here? Supervised classifiers like tree, SPM, and neural nets, and or RL, Q-learning, DQN for online optimizations. So these are the methods we use for these dynamic beam selections and super vectors machines, right? So interference mitigations like machine learning learns beam weights that trade off the gain versus interference suppress, like loss equal to SINR plus lambda into power. So use differentiable surrogates and loss or constraints learning projects gradients, and visuals are before or after radiation patterns showing the null forming on the interferer. So I just write these algorithms like the parameters n beams equal to 8, n sectors equal to n beams, and the trained number of training is 2000, and the n test is 500. So we are generating the synthetic features like, so you will get this true class and the predicted class. So these are the dynamic beams formations in that, like if you see in y-axis, this is the true class or beams, actual beams, and this is the predicted beams, right? So the number of beams forming here is 29 at 1, and at 2 here, and at 2 here you will get 59. But if you see at 3, it will show the overlapping of the beams. That is the problems. It's giving some error. But mostly we are getting the good performance with the help of these algorithms, and its accuracy around 99.80. So with the help of this, we can do the beam selections confusion matrix, and uh, you can say that you can select the beams according to these algorithms. Learning based calibration and channel estimation, this is also one of the most important applications of AIML we use nowadays, because when you design any TX transreceivers, or you can say if I talk about the full duplexes is basically the simultaneously transmission and reception of the signals, and it is very critical and complicated when you design full duplexes, because some to receive and transmit the signals, and you receive the noise also, and you have to cancel the noise. So there are some number of algorithms for the noise cancellations, and zeroing the noise from the signals. So for that, nowadays we use AI or ML models for that particular problem in the full duplexes also. So in that learning based calibration and channel estimations, calibration learning mapping from the measured like gain and phase and offset of the phase and gains and correction vectors, and its benefit is robust to temperature, drift, and manufacturing variations. And method we use here is small NNO regressions like RIS and GPR trained with calibration beacons. And for the channel estimations, you replace or assist the pilot-based estimators with NN regression for sparse channels for millimeter wave and K-band applications. And what are the inputs here is compressed pilot observations, and output is channel coefficients or dominant angle of arrivals or angle of directions. And method we use here, the compressed sensing plus deep nets Lista, CNN, FCN, and auto encoders for denoising. So these are the methods we use here for channel estimations and calibrations. And visuals are block diagrams like pilots, and an estimated channels, and a beamformer. So you can see here the channel estimations, and signal to noise ratio here is like 20 dB. This is the real and this is the antenna index. So you can see here the true channels and least square and minimum square estimation just overlapping. So LS estimation is 0.0710 and MMSE estimation is 0.0093. So this is the down converter design in the system view. I will show you with the system view software. Yes, so in the system view software, basically you can, I can say, you can design the whole systems, right? So in the system view, you can see the performance over all the systems. You can design the up converters, down converters, and up down converters means the full transceiver systems. And you can see the performance while using the different modulation schemes as per your requirement. What type of modulation scheme you want to use? System performance, right? So the down converters here, what we are down converting the signals, it is 29.7 gigahertz, and we it is minus 90 dBm. We are receiving the signals, right? It is very low signals, minus 90 dBm. This is the signal source here. You can apply uh, the multiple source, and you can go here and just check here the frequency and the continuous wave you are applying here, and the power of the signal is minus 90 dBm, which is very low signals, right? So, and after that you are using some low noise amplifiers, you can see, and even you can use some practical low noise amplifiers. You just uh, upload the values here, like gain and noise figure, and these are the parameters of LNAs you have to see, right? And after that you are using these band pass filters, right? Which will pass the signals 29.5 to 29.9 gigahertz. So after the antenna you are using the LNAs, then band pass filters, so that it can remove the undesired frequencies and band of frequencies. And after that we have to down converting the signals. We will use these mixers, and we are using here the multiplier also, right? And this is the oscillators, local oscillators. We are applying the frequency here is 13.65, because finally we need 2.4 gigahertz intermediate frequency at the output. So here is RF signals, this is LO signals, and this is IF. And again we are using this band pass filters, or you can say the image rejection filters, so that you will get the interest of frequency here after the mixture. So then you can simulate this down converter, and yes, uh, you can see the gain, cascaded gain, component by component. So if you see, this is the LNA here, and you are getting here 0 dB gain. Then at this LNA again you will get 27 dB gain. So stage by stage you can see the gain of your subcomponents. And at band pass filters you will lose some gains. At node 6 you are getting 73.9 dB, but at band pass filter you will lose some gain. It is 69.53 dB, and finally you are getting 52.524 dB at the output at the node 3. And This is the cascaded noise figure. You can see you are getting almost the constant noise figure here 1.6. And yes, this is the noise floor. You can see here this is the noise floor, the horizontal line, and these are the intermodulation product. When you see the outputs at the output of the mixture, you will get some components of the frequencies which we don't require. And this is the main signals, right? So this is the intermediate frequencies. At the output we are getting 2.4 gigahertz, and what we received the signals at 29.5 gigahertz, but we are getting 2.4 gigahertz. That's why the down conversion, it is down conversion actually. The frequency is translated from higher frequency to the lower frequency, and the power is we are getting minus 37.45 dBm. We received the power at minus 90 dBm, but now the signal is amplified and you are getting now minus 37.45 dBm power at the output. So this is the down converter, and you can see, so yes, I already explained you this cascaded gain and cascaded noise figure. This is the finally output we are getting. And yes, we use this is the case for up converters, which I will show you the next slide. We have used the components, right? And we wrote the all power consumptions and the voltage and current values. Like this is the model APM 6849 we use, and its power is 0.105 watt and volt is 5 volt, and the current value is 21 milliampere. Band pass filter, we know that this is band pass filter and passive device, it don't consume any much power. And this is the another components. This is HMC 561. This is the model of amplifier, and these are the models, and we just uh, wrote all the power consumptions and the voltage and current requirement for the systems. This is from the data sheet of these components. So this is the up converters design, and I will show you in the system view. This is the up converter. So here we are applying the multiple source. You can see here the continuous wave signals we applied, and it is 2.4 gigahertz, right? And power is 3.5 dBm, because we are just up converting the frequencies. We just applying the frequency 2.4 gigahertz and 3.5 dBm power to the mixture, right? So here we are applying the IF. This is LO, and this is RF. So RF is what? The IF plus LO, you will get RF, right? So, and again we use the band pass filters, and this is driver amplifier, then attenuator, and then we use the power amplifier. So you can see here we use some S2P files in these filters, and you have the options. You can import the S2P file of the band pass filter available in the market. So you can see you can see these files, S2P files, from the websites like DJKey, and some other websites, some other companies provide the S2P files of these, and vendors also provide the S2P files for the simulation purpose. And in system view you have the options to import these files, right? uh, these are the formats you can use to import the files. And so this is the band pass filters, and we have used the S2P files for this driver amplifier, and this is the model you can get, MM3014F. And this is simple attenuators we have used, And this is the we have used the S2P file of power amplifier mmgp 538R. So yes, you can simulate this design, and yes, this is the cascaded gain of this up converter. So you can see this is 0 dB, and after the mixture you will lose the power because mixture is passive and it adds some noise, and it is now minus 9.275 dB, and further it reduces because of this passive device band pass filters. You will lose the power and it is now minus 12.204 dB, and at node 8 it is now 1.958 because of this driver amplifier, then band pass, this is attenuator, and finally at PA you will get 30 dB, right? Because uh, yes, we will see the gain of this amplifier. Yes, so this is S2P file, and finally you are getting 30 dB. You applied around 3.5 dB, and at the output you are getting now 30 dB. So, and we up converting the signals 2.4 gigahertz to, you will see this, right? Now you are getting 19.9 gigahertz. So you have up converted the signals from 2.4 gigahertz to 19.9 gigahertz, and the power you are receiving here is 33.561 dBm. And this is the noise floor, right? So, and this is the response of this band pass filters, which is commercial band pass filters, where we use the S2P files from the vendor, and you can see here you are getting S21 around minus 3 dB, and this is the frequency, center frequency 19.87 gigahertz. These are the responses of this up converter. Now this is the system design. So this is the up converter, and here this is the down converter, and in between them we have used this path loss. We have calculated this path loss actually. So I will explain it with the help of the system view. Yes, so if you see here, this is the another frequency we are applying. So if you see in that system, we have used the multiple oscillator stages. The Here we are using the two oscillator stages, and at the receiver side we also use the two stages of the oscillators. So it depends actually, and sometimes we do the simulations with the single stage oscillator and the multiple stage oscillators if we are getting some benefits in terms of the gain and the power. So here we are applying the frequency 13.55 gigahertz to the local oscillators, and power is 2 dBm, and at this local oscillator frequency will be same and power will also same, right? And we will use some attenuator here. This is mixture 1, where we are applying 2.4 gigahertz at minus 10 dBm, and this is mixture 2, and I will show you the complete simulations. Okay, so this is the cascaded gain. So if you see, we are applying almost 0 dB, and at node this yani that means this at node 20 you will see this is the antenna, right? And this is the path loss between the up converter and the down converter. This is a free space path loss, and you are getting here is 66.21, and just after that this path loss you will get minus 80 dB. So you are losing so much gain here because of the free space path loss. But after down converting, we are using the LNAs and some amplifier stages. Then you are getting minus 31 dB here, minus 80 dB to minus 31. So it's amplify the low signals, right? So this is and so you just applied the signal at 2.4 gigahertz, and then you just receive the power is minus 29.894. So this is the power you are receiving now, right? So if you see the block diagram architecture of this up down converter, you are just up converting the signals from 2.4 gigahertz to 19.7 gigahertz, and now this RF signals at 19.7 gigahertz through the antenna is received and at the receiver, and finally you will get the same frequency. It's down converting the signals to the 2.4 gigahertz. So this is the whole system design you basically consider when you design the TX-RX chain, and uh, you have to check the noise figure and the losses you have to consider at the each stages, and with the help of the system view you can check the losses and the gain at each stages or at each node, right? So so from this figure you can see that you can check the noise floor and the received power and the frequency 2.4 gigahertz, and the power is minus 29.894. So signal is amplified with the help of low noise amplifier. And yes, this is the modulation schemes also use, because if you want to use the modulation schemes in your system, then in system view you have the option here. If you see, this is the block of up converter. So in system view you can just import uh, in this option in the window, and then you can you can create the RF link channel here, right? I have created this RF link, the carrier frequency and the symbol rate, bits per symbols, you can define as per your condition, right? And this is the demodulator, right? This is down converters, and we have used this modulation type is GMSK, right? And GMSK scheme I have used here, and we will see the test and the reference value of bit error rate. You are getting the good bit error rate or not. So it will define your system is performing well or not. So you can see that bit error rate, and this is the comparison between the simulated and bit error rate theory, bit error rate theory 2. So different values according to these we are getting the bit error rate as per our requirement. So this is the way you can use any modulation scheme as per your application in the system view. Just import your up down converters here and just create a RF link between them, and then use the bit symbol rate here, and at here you will get bit error rate of your complete system design. So yes, this is the another talk on the digital beamforming, because I explained you about the beamforming like analog, digital, and hybrid also analog and digital. So this is the digital beamforming, and how you design this digital beamforming in the system view. So this is the digital beamforming for the 4 users. If you see here, user 1, user 2, user 3, and user 4. And here we have used the different weights to achieve the beamformings for the 4 users. And uh, yes, I will mention this software. This is system view. This is the Keysight software, right? For the system design. You cannot design the components like antennas and filters and PAs. You already have these in the library of system view, like power amplifiers, filters, and mixers, attenuators, and TX, RX. You just use these blocks and just check the system performance, and you can import the vendors STP files into that systems, and then you can uh, you can check the practically achievable results and performance of the systems. So this is uh, very good softwares, especially for industries, because before going into the final product, they just check the system performance in the system view. It just give you the lab environment, right? So it will save your time and cost also. So this is the mapping we are doing here, and we are applying the random bits and the bit error rate you defined for the each users. And these are some low pass filters, symbol rates we have applied here, and we have given the phi and theta values and the gain values here, right? And this is the antenna arrays and beam weights we are applying here, right? So you can see that the number of elements in x directions and number of elements in y directions. So you can define according to your requirement, right? So you have the options here. You will go in the antenna configuration, what type of arrays you want to use, like uniform linear arrays, uniform rectangular arrays, circular arrays, rectangular arrays with the triangular grid, and uniform hexagonal arrays. So it has all the options, and what type of beamform configurations you want to use, like shared arrays and non-overlap subarrays and overlap subarrays. You have the options. You can choose from these options the multi-users, and you can apply the window function here to suppress the side lobes while scanning the beams. I explain you, when you just stare the beams, you will get some side lobes into the systems, and then you can use some technologies, some methods to suppress these side lobes, major lobes into your radiation pattern, which consume the powers, and you will lose the powers in the broadside directions. So you can choose the window functions from here, that for example, like Bartlett's, Hanning window, Hamming, and Blackman, generalized cosine ready. So these are the different window functions you can use, uh, right? So we are not using any window functions right now, and these are the beam directions you can define here, thetas and phis. And yes, so okay, and you can define the distance between the elements, right? So mostly in arrays, what we choose is lambda by 2 between the elements. And yes, you can rotate the arrays around them. So you have the options of rotation. So we just using here the reference beam coordinates in dBi, and now we can see the results with the simulations, because it takes a lot of time for the simulation sometimes, and it's very time consuming to explain everything in a short of time. But you can see the real time simulations here. You can see the 3D simulations and how the beams is scanning here. And this is uh constellation. Sorry, what? Oh, okay, I accidentally stopped the simulations. Okay, yes. These are the constellations I and Q diagrams you can see here, and this is the error summaries. So you can see the error vector magnitude of the users and magnitude errors. And this is the table of the error summaries, like error vector magnitude and phase errors, frequency errors, IQ offsets. So this is really pretty good to see the real-time simulations of your systems designs. And yes, so before going into the final product, you can check all the performance and results of your systems. Okay, so yes, you can design the simple phased array in system view also. I will show you in ADS. Uh, yes, this is the simple phased array you can design. Just use a continuous transmitting source, and these are the attenuators, and these are the phase shifters and power amplifiers, and this is the antenna arrays. And you can define your own antenna array here. And uh, yes, antenna configuration, I already told you, you can explain here, and element patterns, which type of radiation pattern you want to see, the isotropic, cosine antenna arrays. And yes, you also have the options. If you designed your antenna arrays in any softwares, any EM tools like HFSS, CST, or any other tool, you can import the radiation pattern file into the system view, and you can integrate your antenna arrays with the whole system design like TX and RX chain, right? So this is very good options here in the system view. So if you see the results, this is the antenna configuration. You can see in X and Y we are using 8 cross 8 64 elements, and this is the beam pattern, right? And here if I change the
इतना ही
beam
कह दिया तुमने,
direction,
कुछ नहीं। आगे तुम मॉरिशस जैसे देश, दूसरे देश में बोल रहे हो जाके कि देश बुलडोजर से नहीं चलेगा। तो सर आपने राकेश किशोर
uh,
I'm
hello.
sorry, sir. Actually, someone unmuted by mistake. Please go ahead.
Okay, thank you. So yes, so you can steer the beam. I just define some parameters here. I show you here. Yes, in system view, yes, this is this software has the interfacing with MATLAB also, right? So you can write your own parameters and algorithms here. So I have defined the signal center frequency and antenna arrays, right? And number of elements in X and Y. So I have write the equations in system view, and just okay. I just changed the theta beam up to 40 degrees, so beam is steering now, and if you apply minus 40, then it will steer the beam in minus 40 degree direction. Yes, you can see here. So it scan the beam in any directions where you want to achieve. And okay, so yes, this is the summary like design of RF transceivers for satellite communications. It involves the very careful considerations like you have to achieve the gain and noise figure, linearity and dynamic range, and all other under strict constraints of the power, size, and radiation tolerance. And by optimizing the transmit and receive chains from the oscillators, mixers to amplifiers and filters, we can achieve the reliable high performance communication links essential for modern satellite systems. And moving forward, advances in semiconductor technologies like miniaturizations and adaptive signal processing and will further enhance the satellite transceivers capabilities, enabling the more efficient and resilient space communication networks. Yes, I want to explain my project, which is very interesting, maybe interesting for you also. This is CubeSat design, which we will launch next year, right? So we are just working on a CubeSat, and it is 3U, and it is designed at Ka band, right, at 29.7 gigahertz, which will be used for to establish the 5G connection between the two sites in Germany. And in that particular projects, I am handling the beamforming antennas panels with the up-down converter receiver chain and TX chain. So we have done some simulations, right? Because we have the limitations of the power consumptions. We cannot use much power. So that when you use any phased array of beamforming antennas, you have to use the beamforming ICs, right? And these ICs consume a lot of power. And for example, if you are using 64 elements and if you are using 4-channel beamforming ICs, right? So 64 divided by 4, right? It is 16. So you have to use 16 ICs for your particular 8x8 antenna arrays. So that is the challenge. You will consume a lot of power with these 16 beamforming ICs. So we are doing a research if we can use a limited number of beamforming ICs and we can achieve the beamforming according to our requirements. So we have done some simulations like this is 2 cross 2 stack patch antennas. This is multi-layer antenna array structures, and we achieved the simulations, right? And we are achieving the gain here around 15 dB. And so we what is the scanning range? It is like -26 to plus 26 degree, and scan loss is 1 dB, right? This is at phi equal to 0, and this is at 19.8. This is at phi 90. The scanning range is -24 to plus 24 degree scanning loss. And if we are designing 4 close to antenna arrays for 8-channel beamforming ICs, so in that particular structures, we can use only single beamforming ICs, right? And we are achieving this uh, gain and the scanning range around -30 to plus 30. And for the other phi equal to 90 plane, we are getting -14 to plus 14 degree. Scan loss is 0.9 dB. And this is 8 cross 8 antenna arrays. If you see the radiation pattern, we are getting very high gain. It is around 25 dB, right? Uh, and the scanning range is -40 to plus 40 degree at 20 gigahertz and 50, and it is at 590 we are getting -30 to 30. So scanning range is increased when you increase the number of elements. You will get the higher gain, but there are some problem in the number of using the higher number of elements. You will get some side lobes also. And this is the solutions we are working right now. If we are using the sub arrays, with the help of sub arrays, we will use uh, two beamforming ICs. But yes, you can see these MATLAB simulations. The beam is steering, but you are getting the major lobes also with the main lobe. This is the challenge we are solving now. And the another thing is, if you are using the 32 subarrays, like if you are using the 4 beamformers, you will get the beam scanning right like -40 to plus 40, and its performance is good as compared to the previous one. And beam steering and elevation is also -20 to plus 20 degree. We are getting some lobes here, but it is manageable. So yes, I have finished my talk, and if you want to discuss about anything from my slides, and if you have any queries, any questions, please free to ask.
Thank you, Dr. Akhilesh. Thank you so much for your time. I think there is one question in the chat box. They have asked, is this software useful for optical signal domains as well?
For optical signals, I don't think so. It is very useful for optical, but I can say it can be useful for RF. Yes, I can say, if because nowadays we are going on the optical transceiver systems, right? So yes, it can be useful for optical transceiver systems also. Yeah, right.
Okay,
And
and
it can be useful for, yes, please.
similar kind of question like for design of VLSI circuits layout.
No, actually, this is not designing tool. This is system design tool. Actually, you can design the whole systems. This is, you can say, this is not like a layout designing and
Circuit layout is
schematic
not
design.
possible, I think, right?
No, no, no. This is system level design actually.
Hmm. I think this is software from Keysight or
Yes,
from
yes. This is from
Keysight.
Keysight. Yeah.
Okay. Cool. Okay, any other questions?
Sir,
But
one
for
question from
layout
my
and
side, sir.
circuit level design, you can use ADS software.
Okay,
This is
sir, we
also
have
from
question
this side.
from one of the participants. So please speak, someone who's speaking.
Yes, sir. Good evening. Good evening,
Good
sir.
evening. Yeah, good evening.
Sir, my question is just about whether we use transreceiver instead of two receiver and one receiver and one transmitter. So which option is best, sir, as per your system guide, making any system, fabricating any system? Transreceiver itself, like in one unit, as a one unit.
Can you repeat, please?
Sir, we are sometimes using a transceiver as a one unit.
Yes.
So is there
Yes.
any difference is that we use individual transmitter and individual receiver? So how it impacts when we make a trans receiver in one unit?
Yes. Thank you for the question. Actually, if you it depends. Sometimes we also use the individual TX and RX, right, at transmitter and individual receiver. But sometimes you have to, if I talk about for the radar applications, right, you cannot lose the signal. You have to simultaneously transmit the signals and simultaneously receive the signals. If you lose the signals and lose the timing, then we can get the threat. So it depends on the application and the risk you can bear, right? For the defense applications, I can say the trans receivers are very important because you have to receive the signals simultaneously while transmitting the signals, right? If you are getting any threat from anywhere. And for the network, for the mobile network coverage also, you need the simultaneously TX and RX, right? So it depends the application. You can use the individual TX and RX, and the compatibility also, even in your mobile phone. This is trans receivers, right? Hello.
Hello, sir. Someone unmuted again. Okay, thank you so
Okay.
much for answering the questions. Actually, sir, they have a test scheduled at 6:30. So,
Okay.
if
Yeah.
you okay, any of the participants having any questions, I'll share his email ID with you all, and then you can connect him directly. Not an issue. Is it, sir?
Yeah. Anytime free to ask, and you can write me an email, and if you any doubt, so I most probably I will answer your questions.
Right. Thank you so much, sir. Thank you for joining us today and giving us the time and apprising our participants about the software. You have also shown the implementation practically. So this would be really beneficial for the people working in antenna.
Yeah. Thank you, sir. Thank you for giving this opportunity so that at least I can share my experience. Yeah.
Right. You have a wide experience in industry as well as in teaching. Good. Thank you so much, sir.
Thank you, sir. Thank you.
Okay, sir. Thank you. You can leave. I'll brief them how to take up the test, sir.
Okay, sir. Okay.
Okay.
I leave the meeting. Yes.